Okay, what we're going to do now is we're going to go over 2009 number 6. This was the one that was on your mock exam that some of you are like, oh, I have no clue how to do this. But hopefully you got points for part A. So if you don't have that in front of you, either go to the, it's up here, you might be able to read it, but you can get your computer out and go to AP Central, Google 2009 number 6. The exams are all online. The solutions are there. Find that question before we go on. All right, we're back. Yeah. So basically it says, in a classroom demonstration, a beam of coherent light of wavelength 550 nanometers is incident perpendicular onto a pair of slits. Each slit, now look at the distance here, 1.2 times 10 to the negative 6 meters. And the distance between the centers of the slit is 1.85 times 10 to the negative 5 meters. So they're really small slits, and they're giving this value here, I think, because they want to see, is the kid just going to be able to plug in the equation? Is the kid going to really understand? I'm not sure. We can look through this. But the kid's not going to know, okay, do I use this? Do I use this? If they just want to plug things into an equation and don't understand the equation. But notice the distance to the screen is 2.2 meters away. So do you think this would be a case where you could use the, let's see.
Whoa.
No, that might be better.
That's
do you think this would be a case where you could use the what do we call it? The small angle approximation equation?
Possibly.
Do you think this angle is going to be pretty small? I mean, in this drawing, it doesn't look like it's going to be very small, does it? But look at the difference between the slits. 1.8 times 10 to the negative 5th, and this is 2.2 meters. This is a case where it's going to make a really small angle, isn't it? Mm-hmm. So you can use a small angle approximation in this situation. So the first question, though, says calculate the frequency of the light. Well, that's really easy. V equals F lambda. It all travels at the speed of light. C equals F lambda. So frequency equals C divided by lambda. 3 times 10 to the 8th, that's on your equation, your constants. You better get that one right. And the only mistake I saw that you all made was you guys were not familiar with nanometers.
It was on the...
And it's also on your constant sheet. People didn't bother to look it up. They just wrote 550 down. But it's 550. Nano means 10 to the negative 9. So you have to divide those two out to get that answer. Hopefully one of you is doing that math already. So it's going to be 3 over 5 is like 0.6, but who's got it? Cricket. Wasting time. All right, well, someone divide that out and we'll get back to that. Now the next part says, calculate the distance between 2 adjacent dark fringes on the screen. Well, let's see here. I'm going to go from here to here. Okay, this is going to be my bright spot, isn't it? And when you get that answer, I'm going to erase this here.
It's 5.454 times 10 to the 14th.
So 5.45, and usually you can just carry it a couple of places past the decimal, and we'll be fine. Times 10 to the 14th?
Yeah.
And that unit, this is frequency, so that it was 1 over seconds. The meters cancel, or we can also say hertz.
10 to the 14? I got 10 to the negative 4, negative 4.
Okay, we're having this argument. Negative 4? Well, she's trying to... Is it 14 or 4?
Negative 4, so that's like...
Okay, it's 3 times 10 to the 8th divided by...
I also don't know how to use a calculator.
Minus... You're subtracting exponents. 8 minus a minus 9.
Yeah.
3 times 10 to the negative 9.
Yeah.
So minus a minus 9. So it's going to be a big number. So I agree with that 14. Because 8 minus a minus 9 is plus 9, so it's going to be about 17. We have to move it over a few places because we had nanometers, 540. So that number sounds righter. More right? Righter? All right. So here's our first bright spot. And we said here we're going to get a dark spot, and then another bright spot, and then a dark spot. We'll call this DS, BS, DS. Now they want the distance between here and here. Well, you're saying, I don't have an equation to do that, sire, so what do I do?
The distances between the dark spots is the same as the bright spots.
Well, the distance between the dark spots is the same as the distance between the bright spots, isn't it? All right, because it's just half wavelength, so all you have to do now is you have to find that distance from here. Now, if you know your equations, you can do it the hard way and find theta by using this equation. M lambda equals d sine of theta. Find theta. Once you know theta, then use tangent opposite over adjacent to find that. Or you can use what other equation did I learn you?
The small angle.
The small angle approximation. This is a good case where you can use it. What's that equation? XM over
L.
And if I'm trying to remember this, I'm thinking, okay, sine of theta is m lambda over d. Tangent of theta is opposite. So from here to here, that's xm over L. So opposite over adjacent equals, oh, but it's not equal, is it?
Approximately.
To the sine of theta, which is m lambda over d. And I'm solving for xm equals m lambda L over d. Now you may, and I haven't looked at the scoring guide, you may want to say, just a note to the grader, the distance, alright, the distance between, what? The first two dark spots
Is the same.
equals the distance to the first bright spot. That's a lot of writing, I don't know. But I mean, just to be sure, so the grader knows, okay. Because I'm sure this problem, there's a bunch of different ways to do that. But this way, if you wrote that and you make a mistake here, you can get partial credit, I think. See what I'm saying? Because if you don't say that and the grader just sees you using this equation, they may not think that, they may not know that you know exactly how to do that problem. So I would go ahead and do that. So xm equals m lambda L over d. Well, m would be basically, I would basically be finding the same distance to the first bright spot, so my m is 1. What's my wavelength of my light?
550.
Well, we have to convert it to meters. 550 times 10 to the negative 9 meters. And L, they give us is what? 2.2 meters. And D is the distance between the slits, which is 1.8 times 10 to the negative 5 meters. Okay, and yeah, and I should say it really is the distance between the centers of the slit. I didn't really say that in the other ideas and the other things we talked about. And then it's just plug and chug. So that is the next part. All right. And I'll let y'all work that out. So the next question, part of it says, the entire apparatus is now immersed in a transparent fluid having an index of refraction of 1.4. What is the frequency of light in the transparent fluid? Okay, so what do you know? How in the world are we going to figure that out? If we stick it in a fluid like that. Any ideas?
It would bend the light, right?
But the frequency doesn't change.
All right, well, the frequency doesn't change when we go from, let's see, one medium to another. But then, wait, let's think about it. This frequency is created by, the frequency is created by the light source, isn't it? I mean, it's created by the rate at which those so let me think about that. So the frequency, if you go, the frequency of the light in the transparent fluid, yeah, frequency doesn't change. Whether you put it, because frequency is created by what is not by what it's in, but by what's creating the source.
We're almost at 10 minutes.
Okay, so frequency.
I mean, like you have 10 seconds.
Okay, well.